Okay, this is going to be our second video on electromagnetic induction. In this video we're going to be covering section 29.3. This is a very, very short section. There are no calculations. We're only going to be discussing Lenz's law, and Lenz's law really only talks a little bit about, well, it kind of gives us another way to look at the direction that our induced EMFs and induced currents will be sort of flowing when we're looking at changing magnetic flux, right? So let's get into it. I expect this video will only take maybe 10 minutes or so. Okay, so Lenz's law, again, section 29.3. So Lenz's law isn't an independent idea or an independent principle. It can be derived directly from Faraday's law, and it's just another way to sort of think about the direction in which our induced EMF and so our induced current are going to point. Okay. Lenz's law states that the direction of any magnetic induction effect is such that it's going to oppose the cause of that effect. Okay. And so what does that really mean? We kind of saw this in the previous video a little bit, but there's sort of two cases that we looked at, so let's look at both of those. In the case where we have a changing magnetic flux through a stationary, not changing circuit. So let's say we have our loop sitting inside a magnetic field, and we're changing the magnetic field such that our magnetic flux is changing. The induced current set up by this changing magnetic field is going to result in a current that's going to cause a magnetic field, therefore resulting in a magnetic flux that's going to oppose this change in the original magnetic flux. So that's quite a mouthful, but basically what's happening is if we have a magnetic if we have a magnetic field set up in such a way through our loop so that our magnetic field is changing, i.e. changing the flux through the loop, then the current is going to set up a different magnetic field that's going to be changing in the other way, right? So it's trying to counterbalance this changing magnetic flux. Okay, so it's not trying to counter the magnetic flux itself. It's trying to counter the change in the magnetic flux, and we're going to see a few diagrams below on sort of how this looks when we draw it out with certain loops, and we're going to look at a slide wire generator again, and that has to do with this sort of second point, which I'm going to discuss here now. If the cause is not this first cause where we're changing the magnetic field and so changing the magnetic flux, if the cause is that we're changing the dimensions of our circuit, if we're changing the dimensions of our loop or the orientation of the loop versus the magnetic field, so basically we're changing A, like a vector A, so we're changing either the magnitude of A or the direction of A in relation to our B field. If this is the case, then a current is set up such that the current produces a magnetic force which opposes the motion of this conductor, right? And we kind of already saw this in the case of our slide wire generator, but I'm going to kind of draw one below, and we're going to talk about that a little more. So the sort of takeaway message from this is this point right here, that induced currents try to oppose motion or change in our magnetic flux. Okay, and so, well, okay, and also I should mention that this oppose in motion is really opposing motion, which is resulting in a change in our magnetic flux. Okay, and so we need to kind of just keep that in mind, right? Lenz's law is just telling us that whatever this induction effect is, it's trying to oppose whatever caused it. Okay. Another way to think about Lenz's law is that it relates directly to energy conservation, and the easiest way to see that is to just look at the slide wire generator problem again. So energy conservation is sort of one of the key principles at the heart of really all of physics. We can't have energy being created or destroyed. It's just changing forms. We can't be producing energy out of nowhere. And so this is why you should always be sort of skeptical of these perpetual motion machines and things like that, right? We can't be producing energy from nowhere. It has to come from somewhere. And so let's take a look at our slide wire generator again. Maybe I should have put an image in here, but I'll draw it. I left myself space here. So this is our slide wire generator. This is some sort of a conductor, right? And so we're setting up a slide wire generator. Let's say we have a magnetic field in the background that points down into the page. I won't draw too many of these, but something like this, let's say. And then, okay, so I guess it would continue out over here. And so we have, and so we also have the sort of slide portion of the slide wire generator, like this, set up here, right? And we define our area vector to point down into the page. Okay, so this is the area vector for the internal part of this loop here, right? And so what do we expect? Let's say we start having this slide wire here moving with some velocity v. We looked at this example in the previous video, and what we end up seeing is that if we move the slide wire to the right here with a velocity v, what's going to happen? Well, we're increasing the flux through this surface, right? So the surface is getting larger, so there's more magnetic flux going through this, right? And the magnetic flux is going to be in a downward direction because of the direction of our B and our A, right? And so we're increasing that flux, and so there's going to be a current, an EMF produced, which then drives a current, which is going to try to produce a magnetic field that's going to oppose this, right? So that's sort of one way to look at this, right? And so we can see that there's going to be an EMF sort of pointing in this direction, and it's going to end up giving us a current pointing in these directions, right? And think about that for a second. Why does it point in that direction? Well, because we have an increasing magnetic flux downward into the page, and so we need to produce, or this current tries to produce, an increasing magnetic flux upward out of the page to try to counterbalance this, right? And if we use the right-hand rule on this current anywhere, we're going to see that this current is producing a magnetic field that points upward like this, right, and out of the page. And so it's trying to counterbalance this exactly like Lenz's law tells us that it should. But if we don't think about the sort of increasing magnitude of A here, right, the increasing size of the area of our loop here, but instead we think about it in terms of the force on this slide wire, well, what forces are sort of experienced, right? Well, we know that this thing has some velocity v. But what would happen if we weren't applying any force to this thing, right? Let's say there were no forces at play here at all, and this thing just kept on moving with some velocity v down in this direction. Well, we would continue to produce more and more EMF, right, or at least maintain this EMF if our v was constant and A was increasing at a constant rate, at least the magnitude of A. And so we would have this constant current, and this current could do work for us, right? So this is a problem, because if we get this thing up to some velocity v, and there's no friction, nothing else going on, if there are no forces at play here, we've just created an infinite, never-ending source of this current, right? Well, clearly that can't be right. So what ends up happening? Well, we have a magnetic force that is preventing us from keeping v permanently, right? So there's some magnetic force at play trying to prevent this motion. This is exactly the second point that we bring up here. There's some magnetic force trying to resist the motion of our slide wire down in this direction, and so to keep the generator actually generating current and so power, assuming that we're doing something with this current, we need to apply a force like this. So this would be our force applied in this direction. And then what is this generator really doing? Well, it's taking this applied force that we're applying in this direction, and it's turning that applied force into an EMF that drives a current, and then we can do whatever we want with that, right? So we're not really producing energy from anywhere. We still have energy conservation. We have an applied force. We have some force resisting our motion. Let's say the applied force is sufficient that at least it's keeping v constant, well then this applied force is all of that force that we're pumping into the system is slowly being turned into current over time, right? And so this is exactly what Lenz's law sort of tells us. It tells us this is kind of an encapsulation of both parts of Lenz's law. We see the part where it's opposing the motion of our conductors here, and we also see the part where it's telling us that we have to be setting up a magnetic field that's going to combat the change in the magnetic flux that we're seeing because of our change in our area. Okay, so that's basically Lenz's law in a nutshell. Here I have a few diagrams that we can look at. We can see what Lenz's law tells us about the direction of these induced EMFs and induced currents. So here we have our loop. Let's say we start off with some magnetic field B, right? And then we start increasing the magnetic field, right? So the magnetic field starts off with this magnitude here from here to here. Like let's say that length represents some magnitude. So we start off with that magnitude, but then B changes. B is now this full length all the way to here. So it's changing over time. We have an increasing magnetic flux going upward through this loop. So we need to produce a current in the loop that's going to produce a changing magnetic field downward that's going to counterbalance, that's going to counteract, or at least try to counteract this increasing magnetic flux in the upward direction, right? And so to do that by the right-hand rule, we have to set up a current running in this direction, right? So Lenz's law just gives us that direction. And I'm going to mention this later. Lenz's law tells us nothing about the magnitude of these changes. It only tells us about the direction. So here in the case of the slide wire generator, it may seem like Lenz's law is telling us something about the magnitude. It's kind of telling us, well, you need to have a force that's at least equal to the force in the opposite direction here, sort of combating your motion or working against this V. But that's not really the case. Really, Lenz's law tells us the direction. Energy conservation tells us that these need to be equal to maintain V, right? Here we have Lenz's law again giving us the direction, but it doesn't. Lenz's law is not telling us that this B has to be, or that this increasing B has to be the same as the increase in B over here. That's going to come from other stuff, which I'm going to talk about a little bit in a second, but we're not going to get into too much here. Mostly that's information that we would get from Faraday's law from our work earlier. Here we have four diagrams. It's basically just the same thing from above, but we can see different changing magnetic fields here, right? So in this case, we're moving the north pole of our permanent magnet toward our loop. So we're increasing the flux going through the loop like this, right? As the magnet gets closer, more and more of these lines are going through the loop, and so the Lenz's law tells us that the current induced in this loop has to set up in such a way that it's producing a magnetic field pointing positively in this direction, so that it's counterbalancing that change in magnetic flux, and that's what we find. We find a current running around in this direction. By the right-hand rule, it gives us a magnetic field pointing in that direction. Okay, right in the direction of this B that they have labeled here as induced. Same idea for the south pole of a magnet moving away, right? So in this case, we have less and less of these magnetic field lines going through the loop, but these magnetic field lines come in with a minus sign versus these ones, right? So same result. We need to produce a magnetic field such that this changing magnetic field is counteracting our change in, well, our negative change in the negative amount of magnetic field or magnetic flux going through this surface, right? So maybe more difficult to say than it is just to think about, but you can see how just flipping the magnet and flipping V gives us the same result, right? In a sense, it's just two minus signs canceling. Same thing we see here if we move a north pole away or a south pole toward. Same idea. We just induce a current going in the opposite direction, which sets up a magnetic field in the opposite direction, which gives us the necessary changing flux, or at least that it's trying to counterbalance that change in flux. Okay. Okay, so a couple of last notes on Lenz's law, and then we'll move on to the next video. So like I said before, Lenz's law tells us only about the direction of the induced EMF and induced current. It doesn't tell us anything about the magnitude, right? We have to use other tools to get at those magnitudes. So it's kind of only a useful tool in thinking about direction. Okay. And so if we kind of follow these ideas, it kind of leads us to think or to see that for materials that are less conductive, like let's say we're talking about different materials of loops. So if we have a copper loop versus a plastic loop or a wood loop or something, there's going to be different effects, right? And it's going to be more or less easy to change the magnetic flux through these loops. So let's say we have a less conductive loop. So let's say we have a loop made out of, I don't know, wood or something, right? So the less conductive the loop is, the less current is induced in this loop, right? Because the magnitude of our current is going to depend on the resistance of the loop. The EMF will still be the same, but you won't have as much current flowing through because you have a more resistive material that the loop is made out of. So in this case, we have quite resistive material, so not very conductive. We have less current flowing through it, and so it's easier to change the flux through a loop made out of wood or plastic or something. The more conductive the material, the more current is induced, right? We have the same EMF, but we have a lower R, and so our I is larger. And because the I is larger, we end up having a harder time changing the net magnetic flux through the loop, right? Because this loop is trying to counterbalance what we're doing. It's setting up a current, and it's able to produce a fairly large current, and so a fairly large magnetic field, or a fairly large change in the magnetic field that's going to oppose what we're trying to do, which is changing the flux through the loop, right? So that's basically it for Lenz's law. There are some additional implications for superconductors, which we're not really going to be talking about. I've skipped over some of that material earlier, and we're not going to talk about it again in this chapter. But for people interested, there's a couple of paragraphs in this chapter on it, and there's a section 29.8, which I may only very briefly mention at the end of this video series. But aside from that, we're not really going to talk about superconductors too much, or superconductivity, so I won't really mention Lenz's law's implications to that at this point. And so with that, I'll end the video here. We'll finish it up, and I'll see you guys in the next one, where we'll be discussing motional EMF.